Okay, welcome everyone to our 5th Scalable Pandas Meetup. I'm so excited to be here with you today. I'm really excited to learn about RAPIDS cuDF, and I'm so grateful to Nathan Stevens for being here to speak with us. Okay, brief recap. So we'll do a brief recap of Meetup goals, have some quick introductions, and then we'll move on to the main event. I think it'll be really great. A quick reminder, this meeting is being recorded, and our plan is, as with previous meetups, to post it to YouTube. So if that presents issues for you, please email me at peter@ponder.io. Okay, so Scalable Pandas Meetups. What are these meetups about? So these meetups exist to talk about challenges to using pandas at scale and then solutions to those challenges. And we're interested in both the theoretical, but I would say there's an emphasis on the practical, on best practices, on stories, on examples, use cases. Who is Ponder? So Ponder is the enterprise-ready pandas company, and it's the primary developer of the open source Scalable Pandas library mode, which actually, as of this week, has more than 4 million downloads, which is exciting. Why did Ponder start these meetups? Ponder started these meetups in order to create a community and content learning materials around using pandas at scale. How often will these be held? These are held typically the 4th Thursday of every month. I believe the next one will be October 27th. And how can I get involved? If you'd like to get involved, you can email me, peter@ponder.io, with feedback or suggestions. We're genuinely very excited about people who want to contribute, present in a meeting, even just like a 5-minute snippet at a meeting about a use case you've encountered, or propose topic suggestions. All right, so moving on to the main event, I get to introduce Nathan Stevens, which I'm excited about, and then we'll turn it over to Nathan for a quick presentation on RAPIDS cuDF, and then we'll have plenty of time I'll ask some questions, we'll have time for group questions as well. So Nathan is Senior Manager for Developer Relations at NVIDIA. Nathan spent before that 6 years at RStudio. And anyway, I have actually a ton of questions about what that experience was like, but I'm not sure if they're as relevant for today. Generally, background in analytic solutions consulting, and then a longtime advocate for operationalizing data science using open source software. Nathan has a master's in statistics, so we're so excited to hear more from Nathan. I'll say on a personal note, Nathan and I had some email exchanges before this, and I was telling him we had both lived in Maryland at one point, and we both now live in deserts. And I had mentioned to Nathan that that I like living in a desert because I feel like in Maryland, the humidity was always trying to destroy my home. And so I feel like my house is preserved here. But then Nathan said, he's like, I feel the opposite, actually. He's like, living in a desert, the heat like melts my hoses outside of my house and like destroys my water softener and stuff. And so maybe, yeah, maybe Nathan's already teaching me that I might be wrong about some tightly held beliefs, and I may end up ruining the day that I left Maryland. Okay, with that, we'll turn it over to Nathan for a presentation on RAPIDS cuDF, and I'll stop sharing my screen and I'll let you share.
Yeah, it's a pleasure being here. It's always really an honor to have the microphone. I wanted to mention that we also have Nick Becker attending here. He's listening in, and we'll chime in with the Q&A. Nick is the product manager for RAPIDS, so got a great bench here. So thanks, Nick, for joining, and it's real good to meet everyone. Like Peter said, I was at RStudio for many years, been a data practitioner. All the things that were in the chat, really resonated with me. The database, the environments in particular, from Matt. Appreciate that, Matt. Environment's such a big deal, and that's not something they really, teach you in school. Like, okay, let me teach you how to fix your, environment. At least I wasn't taught that. Nor was I taught databases. These were things that I had to learn in the enterprise. So yeah, I joined NVIDIA last year, and it's been really exciting to learn the technology. I was excited to, learn about, taking some of these algorithms and scaling them out, making them more high performant, being able to get more out of what you're doing, kind of remove those blockers, that I'd experienced as a data scientist for a long time, when it came to like memory and performance and time management, like, a lot of those blockers are being removed with RAPIDS. So we'll dive into that, and we should just get started. I don't want to go too long either, Peter, so just, cut me off if you need to cut off here.
Sounds great. And I should say too, I'm excited that Nick Becker's here because I've read some things by you, Nick. So it's fun.
Thanks.
Okay.
That's very kind. Excited to be here. I'm gonna let Nathan completely run this show though, so I'll just be listening in and happy to chime in.
We'll do a couple slides. We'll do a couple demos, and then we'll do Q&A. So RAPIDS is. Sorry, still adjusting my screen. Give me 1 second. RAPIDS brings open source GPU acceleration in data science to data engineering. That's the tagline, right? So if you've never heard about RAPIDS before, then RAPIDS is a group of software that runs on GPUs. So it's not just one thing, right? But it's a collection of things. And the area that we're going to spend most of our time on today is cuDF, which is really about manipulating the data, doing input and output, and aggregates, and it's based on pandas. So we'll be talking about that today, but there's a lot more in this ecosystem, right? So we have cuDF ported out to Apache Spark to accelerate Spark. So if you're into Spark already, right, and you're running that on CPU and you want to accelerate that with GPU, that's very doable. Plus, we have all these algorithms for machine learning, graph analysis, and visualization. There's a larger ecosystem with these domain-specific libraries as well. The APIs here are designed to be really easy to use. So we know that people are coming from the CPU world, they're transitioning to GPUs. They want to be able to use their code from the CPU world in the GPU, on top of GPUs. So for pandas, if you're reading data with like read CSV, for example, you're going to have the exact same functions in cuDF, right? It's still going to be read CSV. Same thing with Spark. You're going to have Spark SQL. It's going to be able to run the same type of code, as well as the algorithms for machine learning and graph analysis. So what is RAPIDS ETL? What are we talking about by expandable platform for data science? How is this built? There's a live cuDF library, which is C++ layer to optimize a GPU on top of CUDA. Again, if you're not familiar with CUDA, that's the layer of software that enables the stack to run on GPUs, right? So CUDA is built by NVIDIA. It's free, but it's proprietary software, and then you can build on top of that through live cuDF. And then cuDF is the Python package that gives you the Python API into live cuDF and on top of CUDA. If you want to extend that, there's a Dask cuDF package. We can talk more about Dask if people are interested. And then there's, again, Spark Rapids, repeating myself at this point. Just want to mention briefly the algorithms. So one nice thing about cuDF and the RAPIDS ecosystem is that, like, if you're using cuDF to manage the data, oftentimes you want to build predictive models or do some dimensionality reduction or some unsupervised or supervised learning. And there are a number of algorithms that are accelerated by GPUs with the RAPIDS ecosystem. So some of the most notable that you'll hear is like cuML, cuGraph, XGBoost is fully accelerated in HTB-scan. So the idea with the GPU is that we know that GPUs aren't like the only part of your platform, that there's a lot more going on. You're using a lot of different tools, but all those tools are CPU based. And so our approach has been to accelerate those different tools. So this is a collection of some of those tools that have that are very GPU friendly, let's say, right? They have primary dependencies or primary use cases for doing accelerated data science on GPUs. And so we'd like to get RAPIDS everywhere, right? Get the GPUs into all the workflows, right? That's what Jensen, our CEO Jensen says, like, get it everywhere so that people can use it when they need it. When they get blocked, they can get unblocked and get that integrated into different software packages. So what's new? Everyone likes to always know what's new, right? So GTC was this week. That's the big NVIDIA conference we hold twice yearly. And there was the big announcement from RAPIDS this go around yesterday. I think it was yesterday from Nick's talk actually was, we're making RAPIDS much easier to use with WSL, right? So it's generally available. If you want to use RAPIDS on your laptop, and you have a GPU on your laptop, you can, and you're using Windows, which actually, I mean, I say that's a lot of ifs, but that's like what 95% of users, right? Or maybe like 75% of users. You can do you can access RAPIDS through WSL. So boot up WSL, you can install RAPIDS and use that on your laptop. So don't need a server to use RAPIDS. ARM-based support, right? So ARM chips are becoming much more plentiful in the world, and we're excited about that technology, and we're investing in that technology as well. So we're running RAPIDS on ARM. And then finally, Python for pip. You might be saying, hey, well, what do you mean Python for pip? Can't you use, RAPIDS for pip? And the answer there is that RAPIDS has historically been on Conda, right? So we're now porting that to pip, and you can install RAPIDS via pip, which is what most people would expect. Most new people would expect that, so that's good. RAPIDS is about 3-4 years old now. It's not super old, if I've got the dates right. Nick can correct me, but we've seen a lot of adoption in RAPIDS, and that's been very encouraging. All right, so if you want to learn more, here's a learn more slide. I'll give you the slides and you can click these links later. I'll pause really briefly, see if there's any questions or anything anyone wanted to add.
I think this is great. Yeah, and that's cool that you support ARM as well. It's very magnanimous.
Yeah. Well, I don't know if magnanimous. I mean, it is a little self-interested, but the idea is that we have to. The compute world is changing, right? Like Moore's law. People have been saying Moore's law is dead, blah blah blah, right? And things have plateaued a little bit from the CPU world, but Moore's law is not dead. I mean, if you look at the GPU world, it's far outpacing Moore's law, right? So the question in my mind, and this is just me, it's like, how do you live in this world where CPUs are plentiful, but GPUs are becoming more and more useful, and how do you put those things together? And I think ARM is going to be a big part of that going forward. The different architectures for chips, both CPU and GPU. All right, so let me just jump in here and show again. Not sure how much experience people have with this world, but if you want to get started, there's this really nice page here, 10 minutes to cuDF and Dask, and it walks you through this. Like if you want to put this onto WSL and run this, this will all look very familiar because it's all very Pandas centric, right? So I recommend that. Let me show you what that actually looks like in practice. So to get started, you're going to need a GPU. And the system I'm running, I have 2 GPUs. They're RTX A6000s. They have about 50 gigabytes of memory each. And on top of this, I have the CUDA driver and the CUDA toolkit installed. And you can see all of that here with the different versions of CUDA 11.7. Okay, there's install guides to get you started on that. And then I've got cuDF installed here. This is RAPIDS installed on a PyTorch container on top of NVIDIA's container platform, which is called NGC. And there's 2 ways to do cuDF data. One is through a series object, and then the other one's through a data frame object. And data frame is the most common. You can take the series and put them together into a data frame. So if you just want to look at a series or a column, that'll get you there. Just some real basics here. If you want to start a new data frame, come down and look at this and load up a data frame. And we just have a very simple data frame, right? You can create data frames from Panda data frames. So if you take like build a Pandas data frame and you use from Pandas, this will just convert that data right over into memory. And you can go the other way, of course. You get it from NumPy as well. You can read from CSV, right? So as you would expect. And you've got this really nice API. So that's just going to go on and on. So let me show you what this would look like from like a performance standpoint. We look at the very well-known New York City taxi data. We'll load up cuDF and we'll initialize a few things here. We've already downloaded the data. Go ahead and look at this. This says, okay, so now we've got all three. So we're going to look at 3.3 gigabytes of data. We'll do some functions for reading this in. I'm going to read in through pandas. My memory is this takes about 14 seconds to read in each file. So that'll be about 30 seconds here. And then we'll go ahead and read in cuDF. And cuDF is going to be a fraction of that time. Now I know I actually took the time to play around with Modin a little bit. I would not consider myself an expert on Modin, but I know Modin does a lot of things really well, including reading data. So this will look all very familiar. So 31 seconds there, we'll go ahead and load it in with cuDF. And we're at 2 seconds, right? So that's what you would expect at least 10x performance, right? Like if you're going to move from one technology to another, invest in a GPU, you're going to expect 10x performance. So you can do a whole bunch of fun things with this, right? Like sorting. Sorting is going to be like half a second. And then things that we do really well in here is like the group bys, right? So for the aggregates are going to be like lightning fast in RAPIDS or in cuDF. Yeah, so that was 13 seconds versus half a second. So again, that's 25x performance, right? We'll just do one more and then we'll move on to some modeling. So there's 7 seconds for the group by, and yeah, that was almost instantaneous for the group bys. So for the slicing and dicing, cuDF is going to be very powerful. Now that's just kind of manipulating your data. Like I said earlier, typically what you're going to use your data for is you're going to use it for modeling. So I just want to show a quick example of modeling here. We're going to read in some data. We're going to do some manipulation of the data, right? We're going to do some NA replacements, which I know are important. And then we'll do some splits and we'll go ahead and run this thing. So if you run this on CPU, a GPU on, this is going to be an XGBoost model on CPU. You see that this thing's going to like kind of chug away here, which actually is not bad. It's not too slow. Let me show you what it looks like on GPU. Yeah. So you're talking, I don't know if you're 10x on that one. You're close though. You're close. So anyway, the nice thing about the acceleration of the models is that you can iterate on these much faster. And the idea with the end-to-end workflows with RAPIDS is that, like, yeah, you can manipulate your data and you can build these models and you can kind of go back and forth and do that end-to-end workflow very quickly. So I just wanted to point that out. Now, once you've reached a certain, size limit, you're going to fill up the GPU memory, and you're going to need to look at expanding beyond a single GPU. And that's where Dask comes in. So if you're dealing with a much larger set, I think this Twitter data set is about 26 gigabytes, something like that, 26 gigabytes. That's going to require Dask and multiple GPUs and multiple nodes eventually, like if it gets large enough. So my system has 2 GPUs, and I've loaded, and I have Dask available there. So let's go ahead and see what that looks like. I'm going to do a PageRank algorithm with cuGraph. So and most of this time is going to be spent loading the data. So I shouldn't be talking. Let me get this started. So I'm going to get the client started here. This is what the client looks like. And then I'm going to go ahead and set the data. This is the Twitter data from 2010. I'm going to create the graph. Okay, so this is going to chug away. So what do we do here? We set up a cluster locally. So that's just on my server with 2 GPUs. And I've got a client here that allows me to examine what's going on. So if I'll click on that, I have to rename the IP, my server name. Great. And this is the Dask, page here. And you'll see that it'll like load things up and get things going. The first thing that's going to do is read CSV. And the Dask page is a lot like the Spark dashboard. It has, so many different pages. You can see the GPUs, there's 2 of them, they're chugging away here. And if you get tired of these, they give you this many more, right? So it's like you really go to town on these dashboards. There's no end to the things that you can view. Yeah, we get a profiler. You can see things spiked here on the read CSV. Let's see what we've got here. Okay, good. So read CSV took 50 seconds. And it should be working on the next thing, which would be PageRank. And there's 2 of them again for the 2 GPUs. You can see that we've got things going here still. Yep, things still moving.
Nathan, I'll say that, having demoed some stuff before, it is an extreme vote of confidence in RAPIDS that you are demoing a data set this large live. I just gotta say that's very impressive.
Oh, well, that's thank you for the compliment. So my experience with single thread, again, I'm coming from the R space, right? Like you really start hitting the walls around like 5 gigabytes, 10 gigabytes. That's pretty easy to manage, and you get over that. And I think data scientists just need much easier ways at handling 100 gigabyte files, 200 gigabyte files. I don't know the data scientists necessarily need tools to do a petabyte at this stage. I think there are tools to do petabytes of data, and those are very specialized. But I don't see why I shouldn't be able to just grab, 50 gigabytes of data and just go to town on that. And that's the goal, right? That's the goal, to make that easy. So oh, see, you cursed me. You cursed me, Peter. We hit a hard edge. This was working last night. So we hit something on the number of partitions, the length. Dang it. I'm actually not sure what that issue is. I'm going to have to dig into that. I wasn't getting that yesterday. All right.
No, it's all good. In fact, one of the reasons I said it was like
we didn't finish. We didn't finish.
No matter the outcome, it's an impressive thing to me to do it.
Thanks. Yes, courageous or foolhardy, one of the two. I'm bummed that didn't work, so I'm going to have to get that going again. It was working last night. You mentioned Snowflake earlier. I want to say that we did do some work with a package called Dask Snowflake. What Snowflake does here is it boots up a cluster. It connects to Snowflake, which I don't have the connection set up at this time, but it connects to Snowflake, pulls that data down in parallel into a Dask cluster, and then aggregates that into cuDF. So if you want to pull data, large amounts of data into Snowflake, into cuDF, you would use the Dask Snowflake connector.
Nathan, then, I don't know if you saw in the chat, but one thing that the RAPIDS project and Modin share in common is we both have Dask as a backend. And so Mahesh posted a GitHub issue where we run that same error that you just got from happens to Modin too when it's built on Dask.
Okay. Well, That's nice to know I'm in good company. Thank you. It's not my first live demo that's gone awry, but thank you. Yeah, we moved similar. Okay, I'm seeing it now. Yes. Okay, so I could go on and on, but that's what I wanted to, that's how I wanted to tee up the conversation, because I know you had a number of questions and we wanted to go into your specific questions. So if there's nothing about this, the things I showed, let's jump over to that next section.
Yeah, so I'm gonna take advantage of the fact that I'm the moderator here, and I'm gonna selfishly ask a couple questions, and then we'll turn it over to the audience for some others as well. Okay, so I have so many questions. I guess my first one is about, let's like zoom out and talk about GPUs and CPUs for a second. So I was doing some reading about GPU capabilities and how impressive they are, their performance is for data science workflows. And it's hard to come away from like reading a bunch of articles like that. It's hard to come away not feeling like GPUs are going to have a bigger and bigger share of the sort of data science compute market over the next 5 years. I'm curious to hear your thoughts on that, like, and specifically, like, what do you think GPUs are particularly good at, and what do you think CPUs, like, do you anticipate in 5 and 10 years that CPUs will still have a significant chunk of the market? And if so, why? Yeah, I'm really interested in your thoughts.
Man, I'm really reluctant to take a stab at that, knowing Nick's here, because Nick can say it so much better. So maybe we'll have him weigh in after me. So a couple of things. One is you always pay a penalty when you go from a single-threaded design to a multi-threaded, right? So GPUs by their design are multi-threaded. So, and modems the same way, right? Like it's just going to, it's a law of nature that's going to be more complex. So there's the complexity issue to talk about, and in our case, in GPU case, there's a cost, aspect as well. So what justifies the cost and the complexity? My observation tends to be being blocked, right? Like our CEO Jensen likes to say that we solve problems that other people can't solve. So you get to a point where you just can't like move forward, and that justifies that added cost and that work for the complexity. So an example of that would be like, like those XGBoost algorithms we talked about, right? The TensorFlow, PyTorch. If you've spent time in that on a CPU, it's painful. It's just painful. And people can't do the work they need to, so they look for other alternatives. On the data side's a little bit more complex. We're talking most about cuDF, right? The data side's a little more complex because there's things like Modin, there's things like Spark, right? And so it's like there's ways to still scale out on CPUs. So I think that one we have to be a little bit more aggressive on with GPUs. But I don't know, Nick, do you want to add your voice here?
Sure. Yeah. What I would just add briefly is thinking about GPUs as almost like a nascent technology in the computing world, right? Like, when are GPUs appropriate? Well, I think, and when are CPUs appropriate, I think was the other part of that question that Peter sort of posed. If we look back in the history of like sort of data analytics computing, we can go back to the 1970s and say that people were writing Fortran routines for what eventually became BLAS back in like the mid-70s, which was the sort of foundation of a lot of our computing in Python, of course, but also in other frameworks as well. And that's like a 50-year history. If we go back to like 1972, let's say. So for 50 years, we've been figuring out what can we do on CPUs. And only really since the end of the 2000s have we've been trying to say, what can we do meaningfully on GPUs for general purpose computing? And so looking at it with that perspective, when you have well-defined problems that have known solutions that are time consuming, almost always a GPU will be an effective choice from a cost and a performance perspective. When you have less well-defined problems that are not as well studied or require more user creativity in terms of how to express your logic, it's a little more unconstrained, and relying on that 50-year history of development from the entire world is a much larger asset. And so That's why, for example, we can't do everything on a GPU. You can't run arbitrary code that's been written to work arbitrarily through 50 years of CPU analytics development. So I would just add that little bit of color context, if that helps.
Yeah, that's great. I appreciate it. And just to make it clear too, like right now, I mean, you can go on Amazon EC2, you can get a GPU instance. So like all of these things, you know, someone could finish this meetup today and like immediately go and access in the cloud some GPU and start using RAPIDS. So like this is available for everybody. It's just the tricky thing is right now, like you're saying, typically it's with a known workflow that you know will work because the GPU on Amazon is going to be more expensive than the CPU. So yeah, but that makes sense to me. This like sort of, if the more exploratory the thing you're doing is, sort of the less likely it is that right now the GPU will be able to do it sort of an arbitrary thing, but GPUs are super powerful. Yeah.
Yeah, absolutely. I think I would just add one area. It's not just the exploratory part, because I think GPUs can be great for exploratory work. It's whether the exploratory work requires sort of inventive expressions of code. Like in Python, one of the best things about this Python ecosystem, as well as other data analytics ecosystems, but particularly Python, is that you can be inventive in your expression. Your everything is composable. Any arbitrary function can be applied to any arbitrary data structure. That composability and expressivity is incredible for that exploratory work. It's not always necessary. You can just rely on built-in Dataframe methods or array methods or things like that. But when you need that expressivity, that is a perfect example of when a GPU is going to be a little bit harder to get the payoff. It may still be worthwhile, but it's not as obvious, if that makes sense.
So I was really interested reading through the documentation to see the ways in which cuDF is like extremely compatible with pandas. And then some moments where just the nature of GPUs make it so that some operations either can't be performed or have to be performed differently. So for example, I was intrigued that transpose, you have to have consistent column types is what I read in order to do transpose with cuDF. Can you say anything else about like, what are some moments where a pandas user might have to like be a little surprised or have to learn some new things about cuDF? I know cuDF also supports a few different data types that the pandas does not. So there's, it cuts both ways. There's some things pandas can do that cuDF can't. There's things cuDF can do that pandas can't. Can you say a little bit more about the Venn diagram of cuDF and pandas?
Yeah, absolutely. So maybe I'll start with the second portion first, because it's a little more concise, which is the data type support and what we do in sort of what is like the expanded part of the diagram. There's a significant amount of expansion around different data types. And the reason is that it's focused on enabling not just pandas and the pandas users, but also folks who are coming from a different type of big data processing background. Maybe they're using tools like Apache Spark or Hive or Postgres or other very large scale or columnar databases like ClickHouse and others that have built-in types for things like lists and structs and maps and all sorts of common things that you would need for processing web data or that kind of things. And so cuDF support for that in Python is a byproduct of the desire to support that in these other big data processing engines. And it actually ties in nicely to your question about transpose. Why is there a limitation on being able to transpose data if your columns are different types? Well, the only reason you can do this in pandas is that pandas has a catch-all type for mixed data types. This object type in pandas allows you to have a column composed of one row being a string, another row being an integer, another row being a float. And it's this object type. But under the hood, that's actually very inefficient computationally. In order to make that happen, it has to allow arbitrary Python data structures. We don't do that. Well, it's not really feasible, but we don't do that also an intentional limitation, because in order to support something like that, you have to give up almost all performance meaningfully. So if you're transposing these data frames like that, and you have that scenario, anything you do with that column is going to be really slow, even if you can do it, which can be very powerful. But on a GPU, that's one of those limitations that we put in those guardrails intentionally to limit what you can sort of end up accidentally shooting yourself in the foot, getting yourself in a situation where things won't be useful and you're going to end up spending money on something that won't pay off. Another example of that would be iterating row by row. People do that all the time in pandas. And they do this all the time, knowing it's slow or not realizing it's slow, and then noticing afterward, thinking, wow, I wish pandas were faster, even though I was the one who wrote code that was just slow. Iterating row by row in Python on a GPU would require you to transfer one row at a time from the GPU to the CPU. For most of the time, that transfer is going to be essentially bottlenecked by the act of transferring, not the actual transfer itself. And so if you want to actually make 1,000 individual transfers, not a good use of resources, very slow. So we limit that, instead forcing you to write row-wise operations in user-defined functions. We're actually next week, or in 2 weeks, in our October release, adding support for strings in our user-defined functions, which we didn't have until recently. So you couldn't write like a dataframe.apply using strings efficiently. It just wasn't supported. Now you can do that. It's available as of yesterday in our nightly packages, but it'll be stable in October. So those are some examples of limitations, and most of them are around guardrails and only allowing you to do things that are reasonably performant.
Yeah, that's cool. That makes sense to me. Also, I'm excited about the string support.
Yeah, it's great. We've been playing with it. Sorry, I apologize for interrupting, but this isn't a huge amount of work. Strings on GPUs are complicated, and strings in general for user-defined functions are really, really complicated. And so to make all this possible has been a huge work stream that we've been doing all year. And the payoffs are really spectacular. So I'm excited about it.
Okay, so we have a question in the chat from Matt Harrison about the performance difference between using cuDF and raw CUDA. Yeah, do Nathan or Nick, do either of you want to take that one?
Sure. So the performance difference is enormous, just to be quite honest with you. Anytime you involve a higher level programming language like Python, you basically are saying, I'm willing to give up speed of light performance, full stop. The act of using Python means that you probably will end up bottlenecking your workload with Python. When you're using cuDF, the raw CUDA kernels themselves are actually not that time consuming because they're just so optimized and so fast. Most of the time is spent doing Python things. It's still incredibly fast, but if you wanted to take the time to write your own custom CUDA C++ application, you would see significant performance gains. But of course, that might take you 3 months to do something you can do in 6 hours in Python. So trade-offs, of course.
So I have a question about, so Nathan, you were at RStudio and then came to NVIDIA, and you get up in the morning and you work on Rapids, you use Rapids, you talk about Rapids. I'm interested, what is it about the project that makes you so excited? You have a long history in data science, so you come at this from the lens of a practitioner. Yeah, what is it about the Rapids project that makes you enthusiastic?
Well, a couple things. So certainly seeing things cook, when they're all tuned and running at, Nick mentioned the speed of light. We like to say that at NVIDIA, things moving fast. That's always breathtaking to see. So that's always exciting. And that, yeah, that's a joy. That's certainly a joy. At RStudio, the R world is largely in this exploratory, phase. They do a lot of quick and dirty analyses in R. There's a lot of, development type of, things, scientific computing and whatnot. I think one thing that gets me really excited about working at NVIDIA and Rapids is that there's this production aspect of things, the analytics, quote unquote, in production, right? And that means scaling, so Nick and I have been working on things like topic modeling, right? Which is extremely complicated. You're not going to do that in R, right? That opens up, these great opportunities to do things. Model serving, again, model serving is not going to be done in R. It's going to be done in some other, system and hopefully GPU based, right? We have a product called Triton, which is inference server that's, really well received in the world. And then, there are some other nice things around, NVIDIA just in general, they have this huge autonomous vehicle division, that, you get to play around with and see, and all that, those exciting problems, the omniverse and whatnot. They do some really amazing things at NVIDIA. So that's really exciting to see. But at the heart, I'm a developer. I like data science. I like exploratory data analysis, connecting the data, building those models. Providing those insights and making a difference. And RAPIDS really well suited for all of those things. I do like. It just came to mind, but one thing I learned about the R world is there's this sense of humility, and sense not that the programming language has a sense of humility. It can't, because it doesn't have emotions, but the R language slots into an area where it feels well suited, and that's very comforting, I think, as a user, to use the products. That's where you use product. RAPIDS has some similarities there. RAPIDS is also, in the sense, it's not trying to, it has a broad mandate, but it doesn't try to do everything, right? And so it's going in, if you look at cuGraph is a very good example of this. cuGraph is very targeted, so that we're gonna hit this and this and this, and we're gonna unblock these areas. That's also really comforting, and as you work with RAPIDS to say, okay, this is where you're going to use these tools, and this is why you're going to use them, and this is where they're best suited. So yeah, just a few thoughts.
Nathan and Nick, thank you so much for being here. This was really fun for me. I'm super excited about GPUs for data science, and RAPIDS seems really cool, especially how extensive, how broad the ecosystem is. There's so many different packages. It's not cuDF. There's a ton of stuff that seems to integrate well together, and really fun, really fun. So thank you so much for coming today. We really appreciate it.
Thanks, Peter. Thanks for having us.
Thanks so much. Thanks for having us.